So I want to start today with a quick review of what we talked about yesterday in 9.6. So we'll start with the different types of polar graphs. There are actually 4 different types. The first one that we talked about was the limicons. So a limicon is an r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. The way you identify that it's a limicon would be having a function that you're adding or subtracting a number to. So there can be a b. The b can also be 1 and not be visible, but you'll be adding or subtracting a number, and it can happen on the front side of the function, or it can happen afterwards. You could see something like 2 cosine theta plus 3, and that would still be a limicon. Once you identify that it's a limicon, then you need to identify what your a and b are, because that determines which type of limicon it is. So I would get the a, which is the number that's by itself, over the b, which is the number attached to the trig function, ignoring the sign. So you just take whatever a is, whatever b is, don't worry about the plus or minus between them. And then there's 3 or 4 different scenarios. If a over b is less than 1, so it'll be greater than 0 but less than 1, and this is when you get an inner loop. Then you have if a over b is equal to 1, and this is where you get a cardioid, or a heart-shaped limicon. Next is if it falls in between 1 and 2. So if a over b is greater than or equal to 1, or sorry, not greater than or equal to, just greater than 1, and less than 2, and this is a dimpled limicon. Looks kind of like a lima bean. And then the last one is if a over b is greater than or equal to 2, and this is a convex limicon, which looks like a flattened out circle. So these are from the notes from yesterday, and these are what they look like. Your inner loop has that loop in it. This would be if it's cosine, so that would be a horizontal loop. The next one is the cardioid, or heart-shaped. The next one is the dimpled one. And the last one is that convex one, which is that flattened circle. So this is what they would look like if it was cosine, and if it was sine, they would all literally just be flipped. So they'd all be vertical in this way, or upside down, depending on the sign, the positive or negative sign on it. So you get an idea of all the different types of limicons. Okay, once you've established that it's a limicon, you want to establish what kind of limicon it is, and then go from there to plug in point. Well, then look at symmetry, which we'll talk about in a little bit, and then go into plugging in points to find your actual shape. Okay, then come rows. So the rows curves are r equals a number, so a times the sine or cosine of a number times theta. So r equals a times sine, or r equals a cosine n theta. So the difference between what we had before and this one, obviously what we had before, adding or subtracting something to it. These you are not, but these have a number in between the trig function and the theta. There are 2 types of graphs that have a number there, though. The rows has a number there, but is raised to the first power for the r. That's how you'll tell the difference later. And so we said a rose obviously has petals. Once you identify that it's a rose, you want to know how many petals there are. If n is even, then the petals equal 2n. You double the petals. Double the number to get the petals. If n is odd, then the petals equals n. So whatever number's there. So if I had r equals 4 sine 3 theta, this is a rose with 3 petals. If I have r equals 4 cosine, let's say 6 theta, this is a rose that has 12 petals. The other piece of information that you want to pull out from your rose is what a is. So whatever the number is on the front of it is going to be how far out your petal goes. your maximum R. So from the pole to the edge of the petal is whatever A is. And the first one, well, they're both 4. They would both go out to 4. And then as you're plugging in your points, when you hit that 4, you know that that's your max point. You know you're going from the pole out to that point and then back in. And then obviously roses also have symmetry. You just want to check for that, but we'll talk about that in a minute. Questions on roses? Okay. Then we went to circles, although that was really our first example. And the circle doesn't have anything added or subtracted onto the front. It doesn't have anything attached to the theta. So this is like R 2 sine theta or R 3 cosine theta. These would be circles, okay? There's nothing in between the trig function and the theta. The R is raised to the first power, and there's nothing added or subtracted to the front. You can even have a circle that's just R equals 2, okay? This is a circle with a radius of 2. So sometimes you got the trig function, sometimes you don't. So with a circle, whatever A is, which is on the front, is going to be your diameter. If it's off center, so if it's like this, then this is your A, okay? If it was just R equals 2, then you're going to the radius of 2 in each direction. So your circle would actually be a diameter of 4. So if the trig function's not there, that A is the diameter if it's not on center, okay? But technically it is also still the largest radius, or the furthest point from your pole. Yep.
So if it has sine and cosine, it can't be in the center?
Correct. It would move off of center.
Okay.
Questions on circles? Okay, and then the last one was the lemniscate. And these hopefully are the easiest to identify because these are the only ones that have R squared. So this is an R squared equals A squared cosine 2 theta, or R squared equals A squared sine 2 theta. So I know it's a lemniscate, which is the one that's got the infinity shape. If the R is squared, and then once you know that it's a lemniscate, you want to look at the A squared, which would be part of your actual equation. So if I had R squared equals 25 cosine of 2 theta, then the A squared is actually 25, and the A would be 5. And that, again, is your maximum radius. So if this was that case, then I would go out from 0 or from the pole to 5. That would be the furthest point out. And with these, you're really, again, looking for that one point and then looking for its symmetry to help you on the other side. The lemniscates are always going to be symmetric to the pole. They can also be symmetric to the polar axis or to the pi over 2 axis, but they're always symmetric to the pole. Because you can have them be vertical here, okay? You can have them be horizontal, or the example that we did yesterday, where one curve falls in one quadrant and the other curve falls in the opposite quadrant, that kind of thing. Questions on lemniscates? Yep.
So if we're on the quiz, then we wouldn't have to show work to show that it's symmetric to the pole?
So no, like if it says, it will just say like, what kind is it, right? And then based on the kind, you'll always give me symmetry, but you don't have to actually plug the point in. Is that what you mean? Yeah, no, you don't have to actually show the work of knowing it, because you can use the quick test for the sine and cosine ones, right? When R is not squared, you can use the quick test, and then for the ones that are squared, you know that if I plug in a negative R, it's always going to go back to positive R. Yeah. Okay, so good segue, because the next thing we're going to talk about is the symmetry. So there's 3 different types of symmetry. Okay, the first one is if it's symmetric to the line that is theta equals pi over 2, okay, which we formerly known as the y-axis. And the way we test for this is I would take r theta and I would replace it with negative r negative theta. So if I took an equation in which when I changed both the r and the theta, it goes back to normal or it becomes the exact opposite, then I would know it's symmetric to the pi over 2 line. The quick test for this, which doesn't work when r is squared but does work for the other ones, is if it is sine in your curve. So if I had r equals sine of something, could have a number in there, not have the number in there, it doesn't matter. Because think about what's happening there. So if I had r equals 2 sine theta, for example, and I change the r to negative r, and I change the sine to the theta to negative theta, the sine, S-I-N, when you make it negative, it actually does change it, right? Sine is an odd function. So when I change the angle from pi over 3 to negative pi over 3, it actually changes the sign on the value of it. So this takes on the sign, positive or negative, of that angle. So I know that the left side and the right side don't equal the original one, but I do know that they are the exact opposite of the original one, which would make this symmetric to that pi over 2 line. Questions on that one? Okay, the second kind was your polar symmetry. And for this one, we take our theta and we change just theta. So polar axis symmetry means that this is symmetric to what we used to know to be the x-axis, right? I could fold this top to bottom and it would overlap. The quick test for this, if r is raised to the first power, is cosine. Because cosine is even. If I change the sign on the angle, but I'm looking for the cosine of it, it doesn't change. So if I asked you for the cosine of positive pi over 4 and the cosine of negative pi over 4, they are both root 2 over 2. The sign doesn't change. And that's why the polar axis can use cosine. So in this case, if I had r equals 2 cosine theta, and I wanted to test it for symmetry, I would have left the r alone. I would have made the theta negative theta, and cosine makes that negative go back positive. So I'd get r equals 2 cosine theta. And then I would know it's symmetric to the polar axis. But again, quick test is the cosine is in your equation. R is not squared, but cosine is in the original equation. Questions on polar? Okay, and then the last one is pole. So if it is symmetric to the pole, it's just like your origin. This means you can look at it 2 ways. I can take my graph and fold it along the y equals x line, and if it overlaps and it's symmetric to the pole, I could fold it over the y equals negative x line, and if it overlaps, it's symmetric to the pole. Or you can do both hamburger and hot dog. So I can fold my graph down and left, and it would overlap. And the test for this is I change r theta to negative r theta. So the pole, I change the r. There is no quick test for pole, okay? But if you think about what would make an r go back positive, this would be like a Lemniscate. So r squared would equal 2 sine 2 theta. Something like that. If I plug in a negative r, then this negative is going to go back positive once I square it. So again, Lemniscates are always symmetric to the pole, but they can also be symmetric to the polar axis or to the pi over 2 line, depending on what function is with the r squared. All right, questions on those. So once you identify the type and then get from it the information that you need depending on what type it is, you're going to also want to test for symmetry and then start plugging in your points. So here's the warm-up, okay? There's only 2 questions on it. We did some of the questions yesterday. We'll do some today. Obviously, between the 2 and the homework, you should have covered all the 4 different types of graphs. So this one says, sketch the graph of the polar equation r equals 6 sine 3 theta. What kind of graph is this? It's a rose, right? There's a number in between, but there's not an r squared. So once you identify it's a rose, then you want number of petals, which would be what? 3. Then I want to look for symmetry. I can use my quick test here, right? This would tell me that it's symmetric to what? Good. Everybody good so far? So if it's symmetric to the pi over 2 line, that means that whatever happens on the right-hand side of my graph is going to get duplicated on the left-hand side of my graph. So when I plug in points, I want to plug in things from the right-hand side of my graph and then just flip it over, or left side and plug it. It doesn't matter which way you do. But I tend to start with, obviously, first quadrant, so I would recommend that right side. So I'm going to start with theta being 0, and then let's try pi over 4, make it easy on ourselves, pi over 2, and see if we can't get that rose in those, get that petal from those measurements. So the first one is r equals 6 sine 3 times 0, 6 sine of 0. The sign at 0 is 0, so 6 times 0 is 0. Pi over 4, so r equals 6 sine 3 pi over 4. So this becomes 6 sine of 3 pi over 4. 3 pi over 4 is in my second quadrant. I know it's an over 4, so it's a root 2 over 2 and a root 2 over 2. Sign in the second quadrant is going to be positive. So this is 6 times root 2 over 2. And I get 3 root 2. Oh, the other part that we need from the rose is what A is, right? That's how we know the length of our petals. So if I look back on my original equation, what is A? 6. So I did not get the petal, right? So I know that I have a 0, and I know that at pi over 4, it's 3 root 2, which we're going to approximate root 2 to be like 1.4, 1.2 even. Which would be 3.6. So I'll know I got the edge of the petal if I hit that A, which I did not get. So I'm going to plot that point, but I also now know I need more points. So pi over 4 and 3.6. Okay, so the easiest thing to do is to try to visualize what a 3-petal rose would look like that's symmetric to the pi over 2 line. So I need the same thing to happen on the left side as the right side. So that can be a rose that looks like this, or it could be a rose that looks like this, right? So I know it's gone out and come back in. Now I got to figure out where that happens. So I know I'm going to plug in pi over 2 anyways. I might as well plug that in and see if there's a petal there, and then it would narrow down which of those shapes it's going to be. So if I plug in pi over 2, I get 6 sine 3 times pi over 2, 6 sine 3 pi over 2. So 3 pi over 2 is down at the bottom here. I know that the sign there is -1, so sine times 6 times -1 is -6. So now I know at pi over 2 it's -6. Now when I graph that, pi over 2 is this line, but -6 tells you you're going where? Down. So 1, 2, 3, 4, 5, 6 is my point. So there I just found the edge of a petal. I know it's going there, which means my graphs have to be this way and this way in order to be symmetric to the pi over 2 line. You need to at least find the petal on the right-hand side, though, because your petal can be low or it can be high. It'd still be symmetric. So you can continue to plug in points along that curve, or you can try to think about what you're trying to find. I'm trying to find where the sine of 3 theta would equal 1, right? Because then 1 times 6 is going to give me 6. So how would I get a sine of 3 theta to give you 1? Where is sine 1? Pi over 2. So if I need that to be pi over 2, how do I make theta so that when I multiply it by 3, I get pi over 2? So try pi over 6. If I plug in pi over 6, 6 sine 3 times pi over 6, and I get 6 sine pi over 2. We said the sine at pi over 2 was 1, and 6 times 1 is 6. So now I found where my petal is. My petal is at pi over 6. So I'm going to come over here. This is 6, which means my petal goes out and back in here. And it would be reflected to the left because it's symmetric. So it would go out and come back in over there. If that confused you, like if trying to figure out where the 6 is going to happen, then you're just going to end up plugging in additional points. You know there has to be a petal somewhere in that first quadrant. So you would plug in pi over 6, you would plug in pi over 3 and see which one's going to give you that 6. So your goal with the roses is to make sure you can get those petals, okay? You can use symmetry to duplicate the petal on the other side, but you've got to at least find them. Questions on that one? Okay, example 2 says sketch the graph of the polar equation r equals 3 parentheses 1 minus cosine theta. This is the first time we've seen parentheses, so you want to make sure you do what you normally would do with parentheses and distribute that 3. So I'd get r equals 3 minus 3 cosine theta. So from this, you should know that it's a limison. And A is 3 and B is 3. So 3 over 3 is 1. This is a cardioid limison. So it's heart-shaped, okay? With the cosine being in there, the quick test tells you that this would be symmetric to the polar axis. So everything that happens above the x-axis or polar axis is going to be reflected below. So what this helps us with is to graph only points from the top part of my curve and then duplicate them underneath. So top part, I would start with theta being 0. Maybe do pi over 4, pi over 2, 3 pi over 4, and pi, and see if that gives us enough of a shape. So when I take and plug those in, I can either plug them into the initial equation with the parentheses or right into r equals 3 minus 3 cosine. So theta, if we do the first one, would be 0. 3 minus 3 cosine at 0 is 1, and 3 minus 3 is 0. The next one, r equals 3 minus 3 cosine of pi over 4. 3 minus 3 cosine of pi over 4 is root 2 over 2. 3 minus 3 root 2 over 2. So we talked about before that we want to estimate this. If you wanted to keep it exact, you could keep it the way that it is, but we want to estimate something like when we get square root 3 and square root 2, we want to estimate that. So square root 2 we'll estimate as 1.4. So this is really 3 minus 3 times 1.4 over 2. And 3 times 1.4 is 4.2. And that divided by 2 would be 2.1. So I have 3 minus 2.1, which is 0.9. Then I go to the next one. So r would equal 3 minus 3 cosine pi over 2. The cosine at pi over 2 is 0. 3 minus 3 times 0 would be 3 minus 0, or 3. Then I will continue. R equals 3 minus 3 cosine 3 pi over 4. So I'm still at over 4, which means cosine's root 2 over 2, but 3 pi over 4 is in my second quadrant. So I've now changed my cosine from positive to negative. So this is 3 minus 3 times negative root 2 over 2, or 3 plus 3 root 2 over 2. We just approximated that to be 2.1. So 3 plus 2.1 is 5.1. And then the last one that we have written already is pi. R would equal 3 minus 3 cosine of pi. 3 minus 3, the cosine at pi is negative 1. This becomes 3 plus 3, or 6. Now I want to plot what I have and see if I've got enough to create that curve using the symmetry. So I'm going to go back to my circle, and I'm going to plot the point 0, 0, pi over 4 and 0.9. So I'm going to look at where pi over 4 is, which is here. And I'm going to go to 0.9 just before the 1. The next coordinate point I have is pi over 2 and 3. So pi over 2 is your vertical line. 3 would be here. Then I've got 3 pi over 4 and 5.1. 3 pi over 4 and 5.1 would be there, and pi and 6, which would be here. So then because we said this has polar axis symmetry, all of the points that we just plotted, we can reflect over the axis on the other side. So obviously the 0 will stay and the pi will stay, but at pi over 4, we were at 0.9, which means that 7 pi over 4, I would also be at 0.9. At pi over 2, I was at 3, which means at 3 pi over 2, I would also be at 3. At 3 pi over 4, we were at 5.1. So at 5 pi over 4, I would also be at 5.1. And then we want to connect our points as best as possible. Keeping in mind that this should be a heart-shaped limison. So connecting our points would give us something like that. And there's your heart-shaped or cardioid limison. Okay, you can use the rest of the time to work on the extra practice that's on Canvas, labeled 9.3 extra, or sorry, 9.6 extra practice. And I'll go over the answer to those questions tomorrow. Have a great day.